Algebra 2, Chapter 14, Section 1, Using Subscripts and Sigma Notation. A survey of 9 local gas stations finds the following list of gas prices in United States dollars per gallon. And here's our list. When working with a sequence of numbers like this list, each number in the sequence can be referred to by its index using subscript notation. Okay? So the first entry in the sequence is index 1, so this is a subscript of 1. So G sub 1 is $1.82 per gallon. G4 would be $1.85 per gallon, and G5 equals G9. See, they're both $1.86 per gallon. So that's how we can use the subscript notation to notate entries in a sequence. So let's write expressions using subscript notation for A, the cost of 5 gallons of gas at the second gas station. So that would be 5 times G sub 2, because that would be the second gas station. And we don't have to find the answer, just write an expression. B, the average price of gas at all the stations in the sequence. Well, there was 9 stations, so we would need to add them all up and divide by 9. So we could write G sub 1 plus G sub 2 plus G sub 3 plus G sub 4 plus G sub 5 plus G sub 6 plus G sub 7 plus G sub 8 plus G sub 9 divided by entire sum divided by 9. Now that's very annoying to write all that out. And these kinds of sequences come up so much in certain areas of mathematics that we use a certain kind of notation to indicate a sum over something, and that is called sigma notation. So sigma notation uses the capital Greek letter sigma, which looks like this. So you have a top bar that's very similar to E with like pointy ends on the angles parts here. So we call this sigma because that's the Greek letter. This is the capital Greek letter sigma. And we use that to represent a sum. Now the way we do this is we define an index variable, I, in the bottom beneath the sigma, and we say, so I, this index variable, starts at 1. At the top we say where we end. It ends at n, the number n. Okay, so here the n is abstract, and we'd have to know what it means in the context of the problem. Okay, so then we can say the sum, or sigma, sigma from 1 to n of a sub I would equal, and we're here a is some entry in a sequence, would equal a sub 1 plus a sub 2 plus a sub 3 plus a sub ... plus a sub n. So it lets us not have to write this whole thing out. So what we could have written with sigma notation for our average would be the sigma from I is 1 to 9 of G sub I, and then just divide that by 9. And that's how we can find our average. And that saves us a lot of time. We don't have to write this whole long string of additions out. So let's practice using the sigma notation. First we'll do some expansions. Let's expand this idea. So we're saying the sum from 1 to 5 of I squared, where I is our index, okay? So the first entry would be 1 squared, and we add 2 squared, then 3 squared, and we do this till we get to our last number, which is 5. 4 squared plus 5 squared. Okay? So we say that these n's are inclusive. We include both these numbers in our sum, both the 1 and the 5. Okay, and that's what our sum would be, because this I squared is all in the sum. We could make that explicit with the parenthesis. Okay. There are n airlines. Each airline I owns Q sub I planes and averages P sub I passengers per plane. Write an expression using sigma notation for the average number of passengers per plane across all the airlines. Now it might be tempting at first to try to just average P sub I on its own, but that will not tell you the average number of passengers per plane across all airlines, because some airlines will have more planes than others. So in order to get the full average, we need to find basically the total number of passengers across all the airlines and divide that by all the number of planes. Okay, so the planes is pretty easy. All the planes across all the airlines, we can write it as the sum, or sigma, from I is 1 to n, because there are n airlines, of q sub I. This entire expression represents all the planes. Okay, so we're basically adding all the planes up. Now, how can we get back the total number of passengers that each airline flies? Well, if we take q sub I and multiply by p sub I, that's the number of passengers carried by airline I, because we're multiplying the passengers per plane by the number of planes. Okay, that gives us the total passengers for one airline. So if we add all those up, we would get all the passengers. Okay, so all the passengers across all the airlines would be the sum from I is 1 to n of q sub I times p sub I. So putting all this together, the average across all the airlines would be all the passengers divided by all the planes. So we can take all the passengers, which is the sum from 1 to n of q sub I times p sub I, and divide that by the sum of all the planes from 1 to n of q sub I. Okay, so this is how we can write this average in sigma notation in a pretty dense form. Now we need to write a bunch of stuff out. And this means go across all the, so if there were 7 airlines, we'd have to find each of these numbers multiplied together for each airline, and then divide by the sum of all the planes of all the airlines. Evaluate the sum given this table of the first 9 prime numbers. Okay, so here we have a sequence comprising the first 9 prime numbers, and here they are: 2, 3, 5, 7, 11, 13, 17, 19, and 23. And we're told to evaluate a bunch of different summations. So we'll start here with the sum from I is 1 to 5 of p sub I. So that's just adding the first 5 prime numbers: 2 plus 3 plus 5 plus 7 plus 11. So to evaluate, we need to add those up. So it doesn't say expand, so we need to pull out a calculator. Expand would just mean expand the sum. Evaluate means actually find the answer. 2 plus 3 plus 5 plus 7 plus 11 gives us 28. Here we have a sum from j is 4 to 8. So here this is showing us that what letter we use here for our index could be anything, and it will show up here inside our summation notation. It's the same letter. So we're going to go where j is 4 to 8. So that would be p sub 4, p sub 5, p sub 6. So p sub 4 plus p sub 5 plus p sub 6 plus p sub 7 plus p sub 8. Remember, we include both ends. So p sub 4 is 7, p sub 5 is 11, p sub 6 is 13, p sub 7 is 17, and p sub 8 is 19. So adding all those up, 7 plus 11 plus 13 plus 17 plus 19 is 67. Let's evaluate 3 plus the sum of the first 5 primes. So we already found the sum of the first 5 primes. It was 28. So we're going to find 3 plus 28, that's 31. Okay, so we can reuse our past results to save us time. But now what about the sum of 3 plus each of the first 5 primes? So we're going to add the 3 before we add the sum up. Okay, so this would mean add 3 plus 2 plus 3 plus 3 plus 3 plus 5 plus 3 plus 7 plus 3 plus 11. Okay. Now we could do all this 3 plussing, but if we remember can regroup and reorder this to where we would have all the 3's, 3 plus 3 plus 3 plus 3 plus 3, and then all the primes, plus 2 plus 3 plus 5 plus 7 plus 11. So if we have addition in our sum, we can reorder this addition with the sum itself, with our sigma notation. So we have 3 plus 3 plus 3 plus 3. Well, that's nothing but multiplication. Multiplication is repeated addition. So adding 3 to itself 5 times is 3 times 5. And this sum is nothing but the first 5 primes we've already done, which is 28. So 3 times 5 is 15 plus 28 is 43. That's a faster way of doing it, recognizing that we can leverage the definition of multiplication to make that faster. What about the sum of p sub I doubled, where we go from 2 to 4? So we have 2 p sub 2, which is just 3, plus 2 times 5 plus 2 times 11. Okay, so p sub 4 is not 11. That's p sub 5. P sub 4 is 7. 2 times 3 plus 2 times 5 plus 2 times 7 is 30. Okay, now next one would be, well, let me ask another one here. What about if we took twice the sum from 2 to 4 of p sub I? So then we would have twice 3 plus 5 plus 7. 3 plus 5 plus 7 is 15. 15 times 2 is 30. We get the same answer. Why is that? Well, it's because of the distributive law. We could distribute the 2 across and get the same thing we had up here. Okay, so that's very interesting how if we have a constant multiplied by our things we're summing, we can actually pull that constant in front using the distributive law. That can be useful. This time we have this strange negative 1 to the I. Why would we do this? So let's just evaluate this and see what happens here. So we have negative, for starting with 1, we have negative 1 to the first power times p sub I, which would be p sub 1, which is 2, plus negative 1 to the second power times p sub 2, which is 3, plus negative 1 to the third power times p sub 3, which is 5, plus negative 1 to the fourth power times p sub 4, which is 7. Well, negative 1 to the first power is just negative 1, so we get negative 2. Negative 1 squared is just 1, because we multiply the negatives together, which just gives us 3. Negative 1 cubed is negative 1, so we get negative 5. And negative 1 to the fourth is positive 1, so we get plus 7. So this negative 1 to the I power alternates the sign. It gives us a subtraction every other time instead of an addition. That's what we can accomplish with that, and this actually comes up a lot in sequences in math. So you might see this negative 1 to the index power. Or if the negative 1 needs to be happening on the 3 and the 7, you might see negative 1 to the I minus 1. So you subtract 1 from I to get the powers of I lined up here with the correct positioning. So we have minus 2 plus 3 is 1, minus 5 plus 7 is 2, so the answer is 3. What is going on here? So here we have 2 sigmas. Okay. So this seems really confusing at first. But let's forget about this outer sigma. Let's leave it there and do the inner one. So we would have the sum I is 1 to 3 of p sub I times p sub j. So we'd have p1 times pj plus p2 times pj plus p3 times pj. Okay, by evaluating this first sum. So we got rid of our i's, but we still have this j. Now we do the j one. The sum from j is 1 to 3. We would have p sub 1, p sub 1, plus p sub 2, p sub 1, plus p sub 3, p sub 1, plus, by putting in j as 1, plus p sub 1, p sub 2 for j is 2, plus p sub 2, p sub 2, plus p sub 3, p sub 2, plus p sub 1, p sub 3 for j is 3, p sub 2, p sub 3, plus p sub 3, p sub 3. Okay? So that's a lot. Okay? So if we evaluate all this, we'll get a number. So let's, before doing that, let's actually evaluate. I'm going to take this up here. Sum is j 1 to 3. Let's go ahead and put p sub 1, 2, and 3 in here. So we have 2 pj plus 3 pj plus 5 pj. Okay, so that would equal, when j is 1, we'd have p sub 1, which is 2. So 2 times 2 plus 3 times 2 plus 5 times 2. And then when j is 2, we have p sub 2 here, so it would be 2 times 3 plus 3 times 3 plus 5 times 3 plus, and then when p sub j is 3, we have p sub 3, which is 5. 5 times 2, 2 times 5 plus 3 times 5 plus 5 times 5. Okay? So doing that, we have 2 times 2 plus 3 times 2 plus 5 times 2 is 20. 2 times 3 plus 3 times 3 plus 5 times 3 is 30. And 2 times 5 plus 3 times 5 plus 5 times 5 is 50. Another way of doing that would be to realize we could have pulled the p sub j out, right? So if we had taken this, done some simplification first, we could have made this easier on ourselves. We could say sum is j from 1 to 3 of pj times 2 plus p sub j times 2 plus 3 plus 5, because we've already resolved the p sub i's. In other words, you could think of it like this. And so p sub so 2 plus 3 plus 5 is 10. So we would get the sum from 1 to 3 of 10 times pj. And we already saw we could pull the 10 in front using the distributive law. So we would have 10 times the sum from 1 to 3 of p sub j. Well, this is nothing more than the same 3 prime numbers we summed for over I, which would be 10. So we would have 10 times 10 is 100. So there's a faster way of getting the answer than going through all of the evaluation. We're not going to get much fancier than that anywhere in the book. This section, we don't even need all that work I just did, but we might use that later on as we talk about applications of sequences and series, and especially when we start talking about matrices in chapter 16. Okay, so using the sigma notation, write expressions for twice the sum of the first 5 prime numbers. Okay, so twice the sum of the first 5 prime numbers. Okay, B, the sum of the first 5 prime numbers each doubled. Okay, so we have the sum, sigma I is 1 to 5 of 2 times p sub I. Are these expressions equivalent? Well, they are by the distributive law. We already showed that idea. And the answer is yes. By distributive law. By the distributive law, we can pull this 2 in front, which makes them equivalent. Using sigma notation, write the expression for A, the square of the sum of the first 5 prime numbers. Okay, the sum from I is 1 to 5 of the first 5 prime numbers squared. And B, the sum of the squares of the first 5 prime numbers. So the sum from 1 to 5 of p sub I each squared. Are these equivalent? The answer is no. Okay, and we can just show this. Remember, p sub I is the first 5 primes. We already found the sum of the first 5 primes was 28. So it's 28 squared, which is 784. Whereas the second thing, we're taking 2, the first prime number squared, plus 3 squared, plus 5 squared, plus 7 squared, plus 11 squared. Okay, and when we do all those squares, we get 4 plus 9 plus 25 plus 49 plus 121. Doing all the additions, that equals 208. 784 does not equal 208. So therefore, they're not equivalent. Okay.